Hello, geometry. Welcome back to Mr. Risen's exciting world of analytical and Euclidean geometry. This is Chapter 6, Section 1. We're talking about classifying polygons based on their sides and angles. And then we're going to use the measures of interior and exterior angles of polygons to figure out what kind of polygon they are, what their angles are, and whatnot. Please follow along in the book. You can also look up my good buddy Travis, Tarver, Tuver, whoever. He's got some really good videos to go along. Plus, the online textbook has videos. So you can work with your book as you will follow along the lecture to make sure all of this is sinking in right where you need it. The first thing we need to talk about are what a polygon is. And you need to remember, wait, my remember didn't work. There we go, we'll drag it up here. Remember, a polygon is a closed plane figure formed by 3 or more segments that intersect only at their endpoints. The key is they have to intersect at their endpoints. So for example, that's a segment, that's a segment, that's a segment. That's not a polygon. This little triangle here would be a polygon. If I continued this over here, this would be a polygon, but this whole one figure here is not a polygon because you're not going connecting only at their endpoints. When we start naming polygons, it's by the number of sides. Most of these you already know. You probably don't need to write down that a 3-sided polygon is a triangle or that a 5-sided polygon is a pentagon. But things you might not know are heptagon for 7, nonagon for 9, decagon 10, dodecagon 12. When we talk about sides, of course a side is the segment between the endpoints. Also, the number of sides is the letter n. So that's why for the variable n means the number of sides. Diagonals, of course, connect non-adjacent endpoints. So adjacent endpoints would be A, B, C, D, and E in that order. However, D and C connect, they're a side. D and B do not connect, they're a diagonal. Another example of a diagonal would be, for example, B to E. That's another diagonal. Of course, just like in triangles and whatnot, vertices mean the angle, the corners there. So those are kind of the critical pieces of language. What a polygon is, what a side, what a vertice, and what a diagonal. Now, one of the things they're going to ask you to do is say, hey, identify certain figures as polygons or not, and then tell whether, name them by the number of sides. So for example, here, this is a closed figure. It's definitely a polygon. It has 9 sides, so it's a nonagon. This one is an open figure, so it's not a polygon. This is an arrow. It's definitely a polygon. It's got 1, 2, 3, 4, 5, 6, 7 sides, so it's a heptagon. This is a crescent moon, but since it has arcs, it's not a polygon. It's a figure, but it's not a polygon. Now, also keep in mind that all sides are congruent in an equilateral polygon. Sounds good? All angles are congruent in an equal angular polygon. A regular polygon is both equilateral and equal angular, which means it has the same angle measures and the same side length. So I can think of one right off the bat like a square. Same sides, same angles, right? A rectangle has the same angles, but not the same sides. So keep those things in mind. So it's either regular or irregular. If the sides vary or the angles vary, or the sides are the same but the angles vary, that makes it irregular. And we're going to do an exercise. I'll show you that in just a second. The next thing we're going to talk about is concave or convex. And a polygon is concave if any part of a diagonal, any diagonal, is in the exterior of the polygon. So take a look at this quadrilateral right here. Why is it a quadrilateral? It's got 4 sides, right? But when I connect these two endpoints, now there's another endpoint in between, so these are non-adjacent endpoints, which means I can make a diagonal. If that diagonal is outside the figure, it is now concave, meaning it's caved in, the figure is collapsed, and it's still a quadrilateral. Convex means no diagonals are in the exterior, meaning all the diagonals occur within the polygon. A regular polygon is always convex. And that's what we're looking here in this picture. Basically what we're saying is, hey, when you look at the diagonals, well, first of all, this first one that I'm highlighting here, is it regular or irregular? And you should be saying to yourself, well, the sides are the same, but since the angles are different, it has to be irregular. So this is an irregular convex quadrilateral because all the diagonals are on the inside. It's also best known as a rhombus. All four sides are the same. This one here, of course, is irregular. It is concave because the diagonal is, there's a diagonal on the exterior of the figure. This is definitely a regular quadrilateral, which is also known as a square. And this is a regular pentagon. And of course, any regular figure is convex. I think you're doing pretty well so far. As you remember, and you can read the text above, a triangle is made up of 180 degrees on the interior, right? Well, in this quadrilateral, you can imagine if you make a diagonal starting at one vertex, right? One vertex, and you go to the other one, you end up with two triangles, which means there's really two 180 degree measures in there because each triangle is 180 degrees. So wait, the interior angle measures of the quadrilateral are 360 degrees. Triangle, 3 sides, 180. Quadrilateral, 4 sides, 360. Pentagon, it's got to be 540 because it's, again, 180, 180, and 180. So what does this really lead to? Well, this is where it came from. This leads to your first theorem, and that is the sum of the interior angle measures of a convex polygon with n sides can be found by using this formula, parentheses n minus 2 times 180. And you can see that example right here. Again, a triangle has 3 sides. Subtract 2 from 3, you get 1, meaning there's one triangle. 1 times 180 is 180. And so on and so forth. If you don't know how many sides it has, it's n minus 2 times 180. All right, and now that's the interior. The exterior is a little bit different because when you think about the exterior, it's like you're going around a figure. And what shape am I making when I go around something? Well, that's just a circle, which really means the exterior angle measures of any polygon add up to 360. And that's your theorem. And you can see it in these two examples here. In a triangle, you know the interior is going to add up to 180, but the exterior adds up to 360. Same thing on this pentagon. You know the interior is 5 minus 2, which is 3. 3 times 180 is 540. But the exterior still adds up to 360. All right, this is during class when we take a break and work on some assignments. I'm now going to jump into the next section, which is 6.2, which is all about parallelograms. So this symbol here is parallelogram. And by definition, a parallelogram is a quadrilateral made from 2 sets of parallel sides. There you go. Just made a parallelogram. You like it? Now, the big piece of this, and we're not going to go into a lot of proof of all these components, but understanding the properties of them is the first one. And again, you'll notice this notation. You can read it here, but I'm actually just reading this language right here. If it's a parallelogram, this arrow means then. So if parallelogram, then the opposite sides are congruent, which means AB is congruent to CD and BC is congruent to AD. First property, one of your theorems. Second one, if it's a parallelogram, then the opposite angles are congruent. And you can see that here. A and C are congruent, D and B are congruent. The third one, if it's a parallelogram, then the consecutive angles are supplementary, which means A and B add up to 180. Remember that? Same side interior angles are supplementary. And AD add up to 180. Oh, right. 2 sets of parallel sides. Last but not least is if it's a parallelogram, then the diagonals bisect each other. By definition of a bisector, it means that if BD is cut in half, bisected, BZ is congruent to ZD, and AZ is congruent to ZC. And that's what we're showing here. So now that you see those properties, you can see how you can work out and solve these problems. So for example here, if I want to find the length of Wx, right? Well, Wx is the same as Zy, right? Because if this is a parallelogram, and I didn't write it there, but it is a parallelogram, then you know that Wx opposite sides are congruent. So here it is, 6a plus 10 equals 8a minus 4, right? I'm going to add 4 to both sides and subtract 6a from both sides, so I get 14 equals 2a, and of course a equals 7 when I divide both sides by 2. When I go in and I plug, let me get my little, where's my little drawing thing? Oh man, and the bell. When I plug 7 in here, 7 times 6 is 42, plus 10 is 52. And I can verify that on the bottom as well. The same process is true for the angles here. Actually, let me go through this problem as well. Angle YVW is not congruent to ZWX, but they are supplementary. So if I add these two angles up, 27B minus 9 equals 180, I can actually solve this out. And I'm going to let you work through the math, but what you should get when you solve this problem out is B equals 7. And now you can plug B in back into your equation and say, oh, I can figure out what these two angles are. 9 times 7 is 63 plus 2, and that of course is 65. Hi Haley. I am. What's 180 minus 65? Right, it's numbers, and that's what you have to do to find the other angle. 180 minus 65 is 115, so the top angle is 115. That's kind of the big idea. I only have 2 more problems to do, and what's my time? Where am I at? 12 minutes, let's bust it out. It says the vertices of this parallelogram are, let me grab it, 3, negative 8, 1, 2, 3, negative 8. That's J, and remember, it's in order, J, K, L, M. K, negative 2, 2. L, 2, 6. And the M, I don't really know where M, but it's got to be somewhere over there. And here's why I'm saying that. I know that, I'm going to get out my purple pen here, the 4th coordinate has to be somewhere over there because it's in order. J, K, L, M. It's got to go all the way around. Well, the easiest way to do this is it's kind of like finding slope, but really what you're doing is you're finding the translation to go from this point to this point, and I can apply it down here. The reason I can do that is this has to be parallel to this side, and this length has to be the same as this one. So when I do it, I go up 1, I'm writing 2 with a mouse, 3, 4, and left-handed, up 4, and then I'm going over 1, 2, 3, 4. And so that's what I need to do here. I need to go up 1, 2, 3, 4, 1, 2, 3, 4. Oh, shoot, I'm over 1. But don't worry, I'm a capable person. I can fix it. Right? And then if I actually connect my bars, I know if you guys like it if I connect my bars. Boom. You can see that this is a gorgeous parallelogram. Boom. Look at that. Oh, man. Amazing. What it asks, though, in this problem is, what is the coordinates of M? And, of course, the coordinates are, 7, comma, down 4. The last problem, any questions? Remember, call, email, text. See me in class. The last question is a 2-column proof. It says, given this is a parallelogram, what do you need to do? You need to prove that these 2 triangles are congruent. Well, what 2 triangles are we talking about? AEB. I did ABE, but and CED. Okay. Oh my gosh, that's just my horrible left hand trying to work a mouse. See if you can do better. let's go through it. First thing you do, information given, and the last step, of course, is what you're trying to prove. So statements go on the left, reasons on the right. My first statement is ABCD is a parallelogram. How do you know that? It's given. Now, what I'm going to do to prove these two triangles congruent is use one of my 5 shortcuts. Side, 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 side angle side, hypotenuse leg, you name it. You're going to pick one of those. And I know, because it's a parallelogram, that AB is congruent to CD. So this side and this side are congruent. Sweet. I also know that it's a parallelogram that AC bisects BD and BD bisects AC. Well, that's really helpful because when you bisect something, it makes things congruent, and that's what we're saying right here. This is congruent to this because the definition of a bisector, and this, I'll do it on this side so it's not as ugly. 3 is congruent to that. I should have done that in the first place. By the definition of a bisector. Well, guess what? What information do I have about those two triangles? Triangle AEB is congruent to triangle CED because of side, side,